sir, are you able to see my screen?
Yes, sir. Yes, sir.
Okay, okay. Thank you. So, since the topic is very interesting for this workshop, that is the smart grid, smart devices, smart grid technologies, and for various applications. Definitely, it should be the it should require because nowadays we are using smartphones and a lot of smart appliances we are using domestically, and those with those we will get more benefited with less efforts, and we are able to have means a lot of efficient operations with those appliances. In fact, in domestic use also. So if the things are become smarter for your domestic applications, so that can be done in the field of means research also, and means industrial purposes also. Like in electrical system, we can apply the smart devices in the generation, transmission, and distribution also. Like in distribution, smart metering plays a vital role. In transmission, we will have a lot of opportunities to put the smart techniques so that we can reduce the losses. And in generation, we are having a lot of smart devices that can operate, means that can observe a lot of situations by themselves, and they can interchange the information together. Means in any circuit, if devices can share their information together without putting manual efforts, then the things will become more and more efficient, because they can sense their condition also. Means like what kind of situations, means what kind of you know uh, scenarios they are facing, and they can interchange their data so that they can timely maintain, and a lot of things means you can do. So these things nowadays are very popular, and at the same time, since this is the era of electric equipments like electric vehicle, plug-in hybrid electric vehicles, and a lot of electric equipments are going to be interconnected with the grid. Okay, so nowadays a grid become more dynamic, because a lot of dynamics going to be added. In fact, already a lot of dynamics is added, but in future a lot more dynamics going to be added. Okay, so for seeing these kind of things, what options we are having to maintain its stability, maintain its resilience. A lot of things are associated with the microgrid. So what are the options we are having, and how we can test those things, or how we can check those things, how we can put our efforts to run everything properly in efficient manner. So for that purpose, the option left only is the simulation, because working with the actual hardwares with those kind of setups is really difficult, because nowadays things are a little bit complex in terms of hardwares. Means if you look forward to the circuits, so you will find the circuits are more complex. A lot of uh, means circuits are complex, big, and having high power ratings, high voltage current, and a lot of things are there. So there is a danger of human life. There is a danger of means there is a sometimes more capital going to be in utilized for just developing some small things also. Fine. So avoiding these situations, we need to switch to the simulation part, so that we can develop the things, we can test the things, and we can then at least, means we should have at least some kind of confidence whatever we are developing, so that we can whenever we are going to apply with the hardware, so we can means we can have some kind of results in our mind that okay, this kind of things going to achieve with the certain things. Okay, so first of all, Typhoon Hill, okay, let me finish that what I discussed. So, simulation is the option left to test those things and develop those things, and perform a variety, means check with the variety of scenarios, variety of test conditions, standards, and then we can apply with the actual hardwares. Okay. Now, in simulation, means only simulation is not good enough to test each and everything and check the accuracy. Why? Because simulation is not it's having its own criteria. Means it's a processing power, because simulations is only based on softwares, and that is softwares are going to handle by your system. System means your PC. Okay, so that PC having one processor that is going to process your simulation. Okay, so in simulation, your PC, your processor is going to play, your PC processor is going to play a vital role. So whatever the kind of PC you are having, like nowadays very fast and multitasking PCs are coming, but still they are fast. In fact, fastest PCs are coming nowadays, but those speeds are not good enough for electrical circuits, because in electrical circuits there are three kind of subsystems. First one, that is running on fast dynamics. Second one, that is running on slow dynamics, and the third one is the controller part. Each part having their own space, each part required their own processing speed. Okay, so with only one speed you cannot process accurately all three systems. Okay, so as I have told that in electrical circuit there are three kind of systems. That is the fast dynamics, slow dynamics, and the third one is the controller part or signal processing part, or you can say general mathematics. Okay, so if they require three different processing speeds, it means we need a processor which can run on three different speeds at the same time. Okay, so that is till now it's impossible, but in future maybe you will get a kind of processor that can run on three different speeds at the same time. So what we are having, we need to switch to the multi-processor architecture. Multi-processor architecture means a system which is having multi-processors. One is for fast dynamics, one is for slow dynamics, and one is for general mathematics. Okay, so that kind of system you cannot get into your PC, because your PC is not a kind of a device which is just going to use for just a second. Your PC is not a kind of device which is going to means which is meant to perform simulation only. The purpose of PC is a little different. Simulation comes into it's it's a part, but it's a major task is not to perform simulation. So what options we left? We need to have a specific device which can perform our simulation. Okay, and that is having multi-processor architecture. Okay, so multi-processor architecture you get. Okay, that's fine. Means you switch to the real-time simulators, or you can say simple. You can say simulation to simulators. Simulation is a software. Simulator is the device which is having multi-processor architecture, and the rest is like your PC. Okay, fine. We got the multi-processor architecture. What next we need to do? In electrical system, there is a we cannot calculate the complexity of circuit. It may be quite a small circuit we need to simulate, or it may be quite a big circuit. In fact, you can say a big power system network means multi-area networks are there, and every network having a big microgrids and a lot of DRs are associated. So those kind of systems are not going to those are their calculation is going to be out of limit. The processor which you are going to have means with the single processor. Okay. So what next we need? we need multi-processor, multi-core architecture, so that each core can process, subsystem, and then single processor, means a multi-processor architecture. Single main processor can handle a big network. Okay, so like that, the real-time simulators are developed. Means you can get in real-time simulator multi-processor architecture with multi-core processors. Okay, so in when we talk about the multi-core architecture and multi-processor, means in processing technology, so there are two processing technologies. First one is the parallel processing, and second one is the serial processing. So parallel processing introduced later. Earlier it was serial processing introduced, and now till now we are using serial processing in our PCs. But in advanced PCs, they are switched to the ARM, and in fact we are having ARM processors in our cell phones also. Okay, so in serial processing, things are going to process one by one, and in parallel processing, things are going to be processed parallelly. Okay, so and from which kind of processor we are going to have parallel processing? That is from FPGA. And from which kind of processor we are going to have serial processing? That is CPU. CPU means mostly we are familiar with the Intel processor. So Intel processors comes into the category of CPUs, and FPGAs like Xilinx, Altera, and many other companies are also developing FPGAs like Mentor Graphics, and some other companies are also there. So those are comes into the parallel processing. Now, when we talk about the FPGAs are also having two types. First one is the general FPGA, means the like Kintex, Vertex, Spartan, like these FPGAs. And another one is like another category is the Zinc. Zinc means the CPU plus FPGA architecture in a single chip. Okay, so that is called Zinc, and Zinc is also having the parts like ultra processing and means SoC. SoC, you can say system on chip. So there is a ultra processing. They introduced just a few months back. In fact, I think 1 year back they introduced ultra processing. So it is more faster than the earlier Zinc configuration. Okay, so this is a just a basics of that step by step fundamentals. I have revised that what kind of tools required, and how you can differentiate between the tools, and why we required. Okay, fine. So this is about the real-time simulators. Now, why real-time simulation is required? First thing, we with the real-time simulation we can get our results in real time. Means the processing is going to be similar to the wall clock timing. Means in real-time simulation there are two definitions. Either your simulation is need to run according to the wall means your simulation speed need to be matched with the wall clock timing. Okay, if it is happen, then you can say okay, your simulation is running in real time. Second definition is if any processing if any circuit or any simulation circuit is taking same time to give you the result, means give you the output, means the time required time taken by the actual hardware is going to be same timing you can get in simulation also. Then you can say okay, we are getting results in real time. It's like that. For example, if you are having you means everybody is having a simple fan in their home. So if you switch on that fan and it takes say 30 seconds to get it's a full speed. So same thing need to be happen in simulation also. If you design model same everything is same, switch, fan, supply, everything is same, and switch on the fan, and if it takes 30 seconds to get its a full speed, then you can say okay, this simulation is running in real time, and whatever the results we are getting, it's similar to the physical hardware. This benefit you are going to have, and that you can achieve with the real-time simulators. Okay, so I talked about the smart devices, and means how to perform if what happens if a device can communicate together. So human can speak, but devices cannot. We need to make them speak, and how we can make them speak? By providing some some features like first we need to give less with the some accessories like sensors and some advanced devices, so that it can sense and it can convert into data and it can send. Okay. And also at the same time, if required, it can receive the data and then again it can convert into the device specific language, or you can say means device understandable situation, so that it can understand. Okay. So for that purpose, there are different segments. The first segment is the accessories, which I talk. In that accessories, IoT comes into the picture, some sensors comes into the picture, and a lot of things are comes into the picture. Okay. And next part is the data sending and receiving. So for that purpose, some communication protocols are introduced, like C37.118 protocol and some other protocols. Let me open my screen so that I can show you something, then you can go. Okay. So actually, this is the Typhoon Hill software. You can download. This software is open source. You can download from typhoon-hill.com. I will share the link with original license and lifetime free update. Means you can perform simulation totally free of cost. And if you are faculty, you can give this software to your students also, and they can use this software for their learning. They can explore a lot of things. They can understand easily. A lot of things are there. Okay. So download and install. And for installing the software, what you need to do, you just need to click the Typhoon Hill Quick Start and just open it, and you just go through the document. So what you need to do, let me show you. Just open typhoon-hill.com and then just let it open. Okay, just go to products and then click this virtual hill device, virtual hill. Okay, virtual hill means it assumes means this software is meant to perform a real-time and hill simulation and simulation also. Okay, so it always assumes that this device, this software is connected with hill device. So in absence of this real-time simulator or hill simulator, it assumes your PC as a hill. Okay, that's why it is called a virtual hill device. So from here, you can download your license, original license in your name. What you need to do, just click this and fill the form. A small form you need to just fill it, means your details like name and other details. This is only, and you can get the license in your mail, which you have provided here. And once you got the activation key, click this here, download the Typhoon Hill Control Center software. So once you click this download Control Hill Center software, so what you need to do, register for the virtual hill, or you can click this download the software. Okay, once you click this one, you can get some information also, means a documentation here. You just click it and use this Typhoon Hill Quick Start guide to understand the process of installation and how to download and how to start quick start with this software. Okay, so everything is given, how to import your activation key, and a lot of things are there, but still it's in compact inside. You just open it and you will get some details. Okay, so this is the place from where you can download and learn about this software. Okay, just give me a second. So here it is. System requirement, software download, how to download this software, then this link, then user registration, customer registration, then software installation. Go through with this one, and then licensing. Okay, and then start your simulation. Okay, firmware update is not required, because if you are having hill device, then only it's required. And now how to run the simulation. So everything is given. You just follow this document and you can easily run the simulation. And if you find any issue regarding installation or anything, then you just need to connect with us. Means means you just mail your query on the Typhoon Hill, sorry, hill.support@corps.com. Okay, so I will share the link so that if somebody finds interesting this software, so they can download. Okay, and I will share both the links so you can get the details. Okay, so this is fine. Now next is, okay, so once you install this software here and open, means you will find this kind of shortcut will appear. Just give me a second. This kind of software will appear on the desktop and start also. So once you click this one, you will find home window will appear like this. Okay, so here you will find device manager. Right now I am connected with a Typhoon Hill 402 Hill device, so that's why it is showing all the details. Like a device is Hill 402 connected through USB, status available, device name, serial number, ID, configuration, and then firmware version. Okay, then here it is, the example explorer. So Typhoon Hill is having a lot of examples related to different areas like automotive, communication microgrids, and power system, power electronics, and general power electronics, medical devices, and aerospace, then drives, and a lot of options are there. Like if you open the communication protocols, so you will find some examples related to CAN, DNP3. I was discussing about these protocols. These are required to send and receive your data, because these are specific kind of communication tools, and you will get a lot of information regarding these protocols, and multi-hill, then PC to hill, then means CAN, Modbus, DNP3, C37.118, and some more are there. Modbus, IC61850, Goose, protocol server, then OPC UA for communicating through PLC SCADA. You can use this one, and serial communication for communicating through DSP card, and Sunspec Modbus, and Ethernet variable exchange, DNP3, CAN, generic microgrid. Means a lot of communication protocols are there. If you are interested, just explore the examples that how to use them. And if you are new to into this smart grid technology, you will find examples available inbuilt. Like if you double click, so here you will find examples and related information. Okay, and if you click this open model, so the model is going to be open. Okay, similarly, say you are interested in PMU exchange, means PMU technology for data sending and receiving. So here examples are available. You can just click it and you will find a PMU phasor measurement unit exchange between two hill devices, and how you can communicate with the external PMU, or how you can send your data and receive your data from PDC. Okay, means a phasor data concentrator. So like that, you can explore the examples. Then in documentation, here you will find three segments. The first one is the user guide, second one is the technical notes, and the third one is the API documentation. So in user guide, you will find quick start, software manual, schematic and component library, and means a lot of information are there. You just need to explore. In technical notes, because of you are new to with this software, that's why this technical notes is given, so that you can get the idea that how to model the components available in the Typhoon Hill, like a battery, PV, contactor, and circuit breaker. And if you are interested in thermal modeling of electronic devices, so that option is also available. And a Typhoon Hill application library, this is a specific library. Here you are going to get the details related to the grid connected converters, like wind turbine for WFET generators. This is actually developed by the Professor SM Tripathi from KNIT Sultanpur, and multifunction grid connected converter. This is also is available here. So you can get the detail that how how this model is developed and the related information, and how you can get the results, and what kind of things you are going to have, like active power injection, full active power, reactive compensation, harmonic compensation, and standby, and a lot of things are there. So you can explore the things like that. Okay. So this is about the documentation part. Now next is the license. So about license, if this is green, it means everything is fine. If this is red, it means this is need to be checked. Okay. Now, if you these are four fundamental apps are available. This one is the schematic editor, the place where you can model your circuit using the library components available in the this schematic editor, and then compile. After compilation, your model is going to load on HeliSCADA, and here you can interact with your simulation, your model while your simulation is running. You can get the result. You can communicate through the external hardwares like physical devices, physical controllers. You can communicate. You can send data. You can receive data. For that purposes, in Hill devices, there are analog inputs, outputs are available, digital inputs, outputs are available, and a lot of communication ports are available, so that you can communicate through the external physical devices. Okay. Then Typhoon test IDE. Once you will finish with these two parts, if you required, if you want to test your things which you have developed with some testing scenarios, so this Typhoon test integrated development environment is available. You can test with some standards also that is available in test suite, or you can develop your own scenario for testing your technology which you have developed. Okay. So the purpose of these things are available. This test suite is basically the purpose of these two tools are for pre-certification. What it means, say you have developed one solar controller, PV controller. Okay. PV controller, or you can say MPPT controller, and you have carried your controller to the Tata Power, Tata Solar. Okay, and you are saying, okay, we have developed this new topology. It is very efficient, like blah blah things. You can say. So that means people from Tata company, they will simply ask you what standards you have followed to develop this controller. This is first question. Or what kind of tests your controller has cleared, means your controller is certified or not. So for both the question, you need to find a certification agency so that you can certify your controller. Okay, this is the first thing. Second thing, they are going to charge you for certification. Third thing, it's not necessary that in first attempt your controller is going to certify. Maybe it will certify in first attempt, or maybe it certify in 100th attempt. Okay. So every time you need to pay your time, you need to pay your money also. Okay. For avoiding these situations, those standards are available here in these two tools. You just test your technology controller develop with those standards available here, and pre-certify. And once you will get pre-certification, carry your controller to the certification agency, and it's a 99.9% going to be certified in first attempt. Okay. And with these tools, there are some additional tools are also available, like waveform generator, signal analyzers, script editor, firmware manager, and test and calibration. So waveform generator is for modeling, designing, and testing of PV file, PV generation, and IV PV curve generation. And if you want, you can develop some new technologies also for PV panels. Okay, using this waveform generation. Also, you can do source file generation. You can edit your source. You can insert a lot of complexity in your source, a lot of situations in your source. Like if you want to insert harmonics, you can insert easily. Every options are available here. Then signal analyzer, this is used for analysis of your results. Means you can perform FFT analysis, you can perform you can import data, you can save data, you can edit editing you can perform, and a lot of things you can do in the signal analyzer. Then script editor, this is for smart grid purpose. This smart grid and data communication, this is very interesting tool, because if you like to perform some kind of optimization, or some kind of means library which is not related to the electrical you want to add. So through this one you can add because it supports Python language. Okay, and why Python? First is the it's a word second top language used by the engineers researchers, not only in the engineering field but in non-engineering fields also. Okay, and it finds application in all the areas. Okay, and the third thing is it's having very vast community, means you will get support also all the time. You can get the support from anywhere. Okay, and fourth thing is this nowadays all the simulation softwares are switching towards Python. They are providing Python interface also. These two are related to real-time simulators like Formula Manager and Test and Calibration. So I don't think it's required to discuss. Need to be discussed right now. Okay. So this is all about the home window. What we and this is our company logo. If you click it, you will direct it towards the company's website. This is the version, software version. It is the latest version used, and we are upgrading our software in every 3 months. That is totally free of cost for whatever the people who are using virtual hill device or a physical hill device. For both the cases, upgrades are absolutely free of cost for academic users. Okay, so this is all about the home window of this software. Now I'm just clicking the schematic editor. If you click this schematic editor, you'll find this window will pop up like that. Okay, once you will get this window here, library component are not visible because we didn't open any schematic. So once we will open any schematic, or we will open when we open new schematic, we will find here library components will become visible. Okay, this is the message console. So in message console, whenever you are compiling your model, you are going to get all the compilation report right over here. If you are going to have if you are just a second. Okay, so if you are having any error, so you are going to have those errors listed here. You can modify your model and recompile so that you can check that errors are resolved or not. If you are not able to resolve the errors, you just send your model to hill.support@cops.com and we will help you out to resolve that error. Okay, so let me go through with the new schematic first. So here you can open from file, open new model, or you can simply click this shortcut new schematic. For new schematic, once you click this shortcut, this new model wizard will pop up. And here, if you are just a beginner with this software, you don't need to do anything. Just click next and then click finish. But let me discuss about this one. So here you will get the hill, means if you are connected with any hill device, you will get the information. Okay, the which hill device you are connected with that. Otherwise, you can choose virtual hill. Then you don't need to select here anything. Then here simulation settings. So in simulation settings, only few options need to be selected, like simulation method. So here four simulation methods are available: trapezoidal, Euler, bilinear. You are familiar with these three. Exact is available only with the Typhoon hill. It's not available with the any other software. Okay, it means it supports exact numerical method also, so that you can get a more accurate result. Second option is the simulation time step. So in general cases, people are using auto because they are not having a depth idea that what kind of means how much simulation time step is going to be best suited for their model. So they are generally using auto. But if you are having idea that which time step is best suited for your model, so you can select anyone, and here the simulation time step you can use from 100 nanosecond up to 20 microsecond for your electrical part, and for signal processing you can select 1 microsecond up to 1 second. Okay, so both the options are there. You can perform multi-rate simulation also. Now just click next. I didn't made any changes except this hardware product. Okay, VHIL means virtual hill device. Click next. So whatever the settings we did, we will get information right over here. Okay, right now I am connected with the hill device, so I am selecting this hill 402. Click next and then finish. Okay, so it is going to open. Okay, So once you will click this means once it will open schematic editor. So here you will find the place where you can model your circuit. Okay, and the library components here available. So here you will find only two options, means core and JICE underscore lib. So that is available only in my PC because I have integrated this software, that is JICE underscore lib, that is for spice simulation. So I have integrated this software with the Typhoon Hill library. Okay, so here that's why core means it is the library Typhoon Hill library components, and JICE underscore lib is the this software library component. Okay, so in this core library, you will find circuit breaker toolbox, communication toolbox, contactors toolbox. In contactors, you will find idle, non-idle, both you will find here. Then next is converter toolbox, and in converters, you are going to have inbuilt converters as well as fundamental switches also are available. Okay, so you can use both the options here. Then machines, you will find all machines like brushless, 9-phase PMSM, 9-phase induction, 6-phase PMSM, then 6-phase DFIG, DFIM, then DC machine, DFIM, and a lot of machines are available. You can, depending upon the configuration, you can get all your machines. Okay, like if you select, say, if you are selecting 6 configuration, so you will get some more machines. I'll show you. Just give me a second. Yeah, in machines. So here you will get this brushless DC machine also. Okay, depending upon the type of machines, means it's a criteria. It's a fundamental. It's a characteristic of its a family. According to that one, you will get the machines. And you need to select the configuration, and you will get the machines. Okay. Then next is the measurement toolbox. In measurement, current measurement, RMS, voltage, everything is available. Now, this is the important one. This is the microgrid toolbox. That is specialized, available in Typhoon Hill with multiple options. So let me show you what kind of options you are going to have into this one. So here it is. You are getting, means if you are seeing this library, these library components. So here you are getting information that every DR having one is generic component, second one is generic user interface, then other options are like, this one. Okay, so let me show you what kind of difference you are going to have between these one. Like in PV also, you are getting here PV plant generic, PV plant generic user interface. Okay, so let me show you what kind of benefit you are going to have into this one. Just let me show you. Let me drag this PV plant generic. Then let me drag this PV plant switching. And let me drag this PV plant average. Okay. Fine. So this is, more depth in complexity when you are looking to use this PV plant in the area of power electronics and the related field, power electronics and microgrid. Okay, because this is having IGBT or MOSFET based converters. If you see inside, first let me open its property. So once you double click, you will find you need to put the data only. Means the ratings you need to fill these parameters with the values like general values, power rating, voltage rating, current rating, frequency and switching frequency of inverter, DC nominal voltage, area, efficiency, PV efficiency, then filter values, and rest other are the controller values. Okay. Now, if you want to see its internal structure, just go to mask and look under mask, and you will find here a complete circuit is available. Means why these libraries are available in build? Because if you ask people who are working on the microgrid, they all say they are using my PV, wind, diesel, and battery energy storage system, and like those things. Okay, so for them, these are available in builds, and if you want to do any modification into the internal structure of this component, so you need to do first unlink this component, and then only you are allowed to make changes of internal structure of this component. So here you can see the control logics are there, like a grid follow mode or grid forming mode, then duty cycle and MPPT. Everything you are going to have into this one. Okay. you can edit this model whenever it's required. You can edit your this model, but before that, what you need to do, unlink this model. Okay, so this is IGBT, or you can say conventional switches based model. That's why it is called PV plant switching. Next is the average model. This is means develop for the people who are looking to develop microgrid more towards the power system side, because their more intention is more towards the power system side. So we all know that means IGBT MOSFET based switches required more processing power to calculate its state space equations and give the results. Okay, but in general, average switches means like a normal switches or signal controlled variables are there. So those like this here, signal controlled sources are there. These are controlled by the signals coming from here. Okay, so they are giving output. So they required less processing power to process. So so that you can utilize the remaining processing power towards your main area of focus. Okay, towards a more focused area. Okay, so depending upon your type of, means your application, like means which kind of microgrid you are developing, and where means on which side your intention is. So you can use these components, like this is average, this is switching. Now one more component is available, that is the generic component. This is a more advanced component. Means if you develop everything and your intention is only to test with some advanced features. Okay, like if you double click to open, so you just need to put the data, then PV, and then you will find option to test with some grid codes, like a low voltage right through, low frequency right through, high voltage right through, high frequency right through, and also with the multiple countries options. Means the countries where these codes are available, you can test with those situations also. Okay, or you can create your own by putting you can create your own standard by putting these test points. Okay, and rest details you can put here. Then grid extras, you will find here details. So like that, depending upon the type of testing or type of development you are looking for, you can use these components as per your requirements, and uh, they use their own required processing power. Like this require more processing power, this require less processing power as compared to this one, and this require far less processing power as compared to these two. Okay, so accordingly you will find wind, diesel, battery, and back-to-back converter for application to the DFIG and some other applications also. So like that, this microgrid library components are developed. Okay, I hope you got the idea. Next is the converters. So here you will find the converters are available. Now, in why these converters are available inbuilt? Like if you drag the boost, you will find this is available inbuilt. If you drag this Herrick converter, you will find this is also available inbuilt. If you drag this NPC leg, you will find neutral point clamp converter. SAPIC is available inbuilt. So these converters are available inbuilt. Why these converters are available inbuilt? See, when we talk about the people who are using converters into their research, so more than 90% people say they are using conventional converters. Conventional means those topologies which are already developed. So for them, these converters are available inbuilt. Means they don't need to put IGBT, then diode, and then connect. So then only they can work, or they can design these things. Okay. So for them, what we did here, we designed these converters in this manner that they are going to require less processing power. Okay, means our main focus is to reduce the requirement of processing power. Why? Because softwares are having infinite limits, but the real-time devices are having some limit. Whatever the means, it's a, you can say it's a supercomputer. Okay, but still that is having its own limit. Means it can calculate up to this range only. Okay, so accordingly you can compare the Hill devices also. They are all having their own limit. Okay, so like that you can compare these things. So here these are developed to require less processing power. And the second thing, you can find one more option here, that you don't need to design, means we have given option, choice is yours. If you want, you can design career and reference both. But if you are not interested to develop career, so inbuilt career option is also available. What you need to do, just put the data like career frequency up to 200 kilohertz, you can simulate into Typhoon hill. Okay, with time step down to 100 nanosecond. Career phase offset 0.0, dead time period 5 microsecond, reference minimum maximum execution rate. This is the career modeling. You can put the career modeling, you can select variable career frequency also, it's required if required, or you can select the fixed career frequency. Okay, and say you want to perform thermal loss calculation. So what you need to do, just select the configuration number 4, because in this configuration here you will find the details about the configuration, that how to select. Right now we are running out of time, so I'm not able to discuss these things in detail, but I am just letting you know that why I have selected the fourth configuration. So here it is, you can get the converter power loss calculation. No. In fourth configuration it is yes. That's why I have selected the fourth configuration. And let's click OK. So here you will find the option to calculate, means for thermal loss calculation. If you check this one, so here you will find put means load your loss data file, loss XML file for IGBT or MOSFET, and for diode also. Or you can create your own data. Means you can fill this parameter, and you can create your own loss calculation strategy. Okay, so like that you can get this. So these options are available in build, and you can utilize as per your requirement. Okay, some more library components. I am just two of more I like to discuss, and then I'll run some examples. Okay, so here one is the test suite. Here you will find anti-islanding. Means if you want to test your microgrid with anti-islanding mode, you can test DC meter. You are going to have here for DC microgrid application, and some other. Here are two faults are available. This is the grid fault, and another one is the dynamic grid fault. So what difference? Both are same in fundamental concept, but the difference is you can change the fault scenario in this dynamic fault by from SCADA by changing these numbers. Okay, so according to the fault which you want to create, you just select the number, and you can create that fault. Okay, while your simulation is running. Sorry. Next is the grid simulator you are going to have with this one. So these are available in test suite library. And at last, just a second, control delete. At last, next is common for you. You are well aware with these components. Next is signal processing. So here you will find a lot of components available. You can design your own. If something is not available, you can design using this signal processing, like PID, PWM moderator, SV, PWM reference generator, PLL, and transformations. And if you want to import your controller from other softwares, so for that purpose, functional mockup unit is also available. If you double click it, you can import your controller from any software. Okay, using this FMI. And some other options are also available, like if you want to use some optimization technique, or you want to write, you want to add some threats, or you can say hacking you want to create in smart grid, or you can you can create some attacks using scripting. So this is the component where you can use that one. In fact, my paper, event trigger super twisting sliding mode control for smart grid application, which I have published, means we have tested. I have tested with Mr. Vivek Chauhan, who is pursuing a PhD from IIT BHU under Soumya Mohanty sir. In that one, we have used this C function box set to create some attacks, and we have developed some attacks, and then we prevented our grid to those attacks. Okay, so like that you can also put, or you can create some you can put optimization techniques like PSO, PNDO, or some other algorithms. Also you can write over in C C codes, general C codes, not in typical C language. Okay, some other also available like power measurement and power system toolbox. So here, just go through with that. So this is all about the library components. Now let me open quickly a very simple example, that is the electric vehicle example. Let me start with that one, and then I'll discuss about some other features also. First, let me run this model. Okay, so this is the electric vehicle model. You will find available inbuilt in Typhoon Hill software. Here, this is the grid with the residential load. This mask is created. If you double click it, you will find the information that this subsystem includes the power grid and the 20 kVA residential type load. Okay, and if you want to see inside, just right click and go to look under mask. So here you will find this is the grid with this RMS voltage, and this is the our residential load. So this is the 20 kVA residential load with nominal voltage level is 240 volt with frequency 60 and power factor 0.95. Okay. And these are the grid impedances added with the grid, so that we can put something. So okay. Now this is our charging station. So this consists a battery inverter that is going taking a power from grid to charge means sending power to the grid and receiving power to the grid. So this is the battery inverter. You can say this is the charging. So if you right click and if you go in, let me first double click. So this is having 175 kVA rating, and with voltage 240 volt, DC link voltage 400, and the rest other parameters switching. It is running on 2.5 kilohertz switching frequency. Okay, these are the filter values. These are the controller values. Then next, if you want to see the internal structure, just right click and go to look under mask. So here you will find this is completely developed model. Now, if you want to make any changes, just right click and make the changes. So this is the inverter used here, and this is the carrier frequency. So, and these are the logics. So all the measurements, converter measurement block is here, grid measurement block is here, and this is our control logic. So if you go in depth, so here some different control topologies are available depending upon the requirement, like current mode control, then voltage mode control, then synchronous check is performed, ABC DQ performance transformation is there, and then PLL for converting your ABC parameter to DQ. Okay, and then changing the control board, some trigger options are developed here so that it can change automatically as per requirement, and this is the duty cycle. Okay, so this is going to be going to the inverter. So this is our charging station. Next is this is our vehicle. So if you go inside, let me first double click to this one. So this vehicle with 270 kilowatt induction motor and the 250 ampere hour lithium ion battery. The powertrain control module implements regenerative braking. Okay, so why those things are created? So that it can transfer from vehicle to grid, V to G, or grid to vehicle, both way. Okay, in this example, you will find both way power is transferred. Just right click, go to look under mask, and here you'll find this is the our lithium ion battery with a nominal voltage of 400, capacity 250 ampere hour. Initial SOC is 80%. If you want to see the SOC curve, just click it and you will get the SOC curve. Okay, and signal processing part. So state of charge output port, this is right over here. It is checked so that it can display here, and we can get this SOC as an output at SCADA. Okay, so this is about the battery. Then this is inverter, which is running on 20 kilohertz switching frequency, and other things are you can explore. Then here the LC filter is used, and this is the grid three-phase measurement block, and here we are measuring 3 currents with 1 voltage. Okay, if you double click it, here 1 voltage measurement and 3 currents measurement here. Then this is our induction motor. electrical, what you need to do, put the electrical parameters, mechanical parameters, and load. You can load this machine with the external load also by selecting means a type of, first select type of load, it's a torque or speed, say torque, and then load a pin. So analog input pin is available on Hill devices. Select the pin number, connect your load with the selected pin number, and then you can load this machine from the external side also. Set the gain value if required, and set the offset value if required. Okay. Then feedback. So this is going to be encoder. Means if you want to send the machine data, or you can communicate with the physical machine through your simulated machine. So you can use this encoder so that you can get some kind of feedback like external. So select the pin number. So here are 16 pins are available. Say I am selecting this 6 number pin, or resolver gain. You can put the gain and then type, select the communication type like encoder protocol, ENDAD is SSI. Okay. Then snubber output, if you required for developing your controller, you can make this true. Right now here true is selected, that's why these two terminals are available here. Okay. And fault you can create in simulation like inter-turn short circuit fault or fault location. You can select the phase A, phase B, phase C, depending upon your choice. You can select any. Okay. So this is about the vehicle. Now let's compile this model. Once we will compile this model in message console, we will get the detail. Okay. Till that this model is compiling, if anybody is having any query, they can unmute and they can ask. So here in compilation report, you can get the information that how many cores are utilized. So here in this model, 2 cores are utilized, and then you can check the core detail information that how much capability they are utilizing. Maximum limit is given here, and utilized unit limit is given here. Okay, and this model is running on 1 microsecond time step. And then see the codes are generated automatically for since we are using Typhoon Hill software with the Typhoon Hill simulators. So you don't need to worry to perform a real-time simulation by generating codes, because when you are using okay, just a second, I think I have connected wrong device. So let me change the license and then I'll run this example. So it is just going to take a few seconds time. Let me quickly change the import license. Okay, so let me close this one and let me reopen. So it is remain connected with the internet. So the license is going to be updated automatically. Just give me, yeah, license is updated. Now let me quickly open this schematic editor. Okay, so it's open. Let me quickly open this example, electric vehicle. Okay, let me quickly compile. Till that, let me post the link where you can share your queries. Hill.support.
If anybody finds any difficulties to work with this software or downloading or installation, they can uh, send their query on hill.support@corps.com. Okay, let it compile. It will take hardly few seconds time. So generally, what steps need to be do when we perform real-time simulation is from simulation to real-time simulation, because those companies who are manufacturing simulation software, they are not manufacturing real-time simulators. So what we need to do, we need to make our model compatible with the real-time simulators environment. Okay. So for that purpose, what options we are going to have in the software, that is only generate the codes. Without codes means we cannot take model as such, means we cannot load a model developed in different software to the different simulators. Okay, so what you need to do, you just need to generate codes, because they can understand the codings. Okay, so for that purpose you need to do a lot of adjustments, because say we are more familiar with the MATLAB. So once we want to run our model in real-time simulation from MATLAB, so what we need to do, we need to switch from continuous to discrete. First thing. Second thing, we need to do some adjustment. Means we need to pass some errors in terms of warning. Okay, because when we are converting from continuous to discrete, a lot of assumptions we need to take care. After that, we need to use embedded coder to generate codes. So you need to do some settings over there also, and depending upon the type of hardware processor is means real-time simulator you are using, you need to generate your codes. If you are using FPGA, you need to generate codes in VHDL. If you are using Intel-based processors, Intel-based devices, then in that case you need to generate your codes into C. Okay, and sometimes both the codings are required. Okay, because as I have told you, multi-processing architecture. So for that case, you need both the kind of codings. Okay, so avoiding those situations, because as I'm telling you the step by step that how you can perform real-time simulation from simulation to real-time means simulation to real-time simulation, generating codes and a lot of things. Typhoon Hill, passes those steps by providing their own software. Okay, so that you don't need to worry about this part. It is automatically done by this software. Codes are generated for your slow dynamics parts. That is going to user CPU, means the CPU that is ARM processor. So that is available. Let me show you. If you open the documentation part of this software, here it is, and open this schematic editor. So in schematic editor, if you click this system requirement, and then sorry, in system requirement now, if you click this modeling principles, and then system signal processing modeling principles, so here system architecture, just give me a second. System architecture, here it is. So here you will find this one, that this is the multiprocessor architecture. So here in Typhoon Hill, there are 3 processors used. Generally, in any real-time simulator, there are 2 processors they are using. But in case of Typhoon Hill, we are using 3 processor-based technology. One is user CPU, that is ARM processor, that is processing your signal processing part as shown in this diagram, in this circuit. And another one is the system CPU, that is the used for processing of slower dynamics like engine generator, RMS voltage measurement block, RMS current measurement block. And next one is the Typhoon FPGA solver, that is processing fast dynamics part. Okay, so all 3 are processing in their specific speed, and then they are interchanging data in at a common platform. Okay, so this is the Typhoon Hill technology. Okay, so accordingly, you will get the compilation report here. Like see, starting code generation for user CPU and compilation, then starting code generation for system CPU. Okay, if you are having any slow dynamics part there. Okay, so it is compiled now. Since I'm connected with the Hill device, therefore the model is automatically loaded onto Hill SCADA. This is this window which is going to automatically pop up after compilation. That is named as Hill SCADA. So here you will find this Wiget library. I will give the brief about this one later. First of all, since we are running inbuilt example, so what we need to do, just click open panel. But if you are working on with your own model, so in that case you just need to click this create new panel and you need to design the panel. Okay, so I like to go with the open panel. So it is going to open. Let it open. So this is going to open. Let me enlarge this window and best fit the zoom. Okay, so this is the SCADA panel. Here you will find the information about the vehicle. Here you will find the information about the battery and power transferring mode and battery SOC. Then here you will find the status, means what kind of things are going to happen, like the vehicle is connected with the charging station or not, and the direction of power flow. You can get the information right away. Let's start the simulation so that you can get the idea. So I have started the simulation. Right now nothing is happening because nothing is on. So let's start some ride first. So just double click the vehicle and I'm starting the engine, or you can say the vehicle. So let's once I have started the vehicle, let's give some throttle. So I'm just giving a small amount of throttle, let's say 3. Okay, so see some speed is coming. Let's move to the 30. Okay, so here speed is increasing and see the timing also. Everything is running in real time. Okay, now let's give some more throttle. Let it stabilize, then we will give some more throttle. Okay, so now it's a constant. Let's increase up to 70. See, speed is increasing and the power is also increasing. And this is the torque, electrical torque, and this is the load torque. Okay, and this is the battery SOC. You are getting information about the battery SOC also. Okay, now let's give 100% throttle. So now this vehicle is going to run on its full speed. It's around 220 kilometer per hour. Okay. And total distance we have traveled within this one and approximately 2 second is approximately 3 kilometers. Okay, and the RPM is here. You can get the information. Now let's get back to the here. So see, right now this vehicle is moving. That's why it is energized by this battery pack, or you can say lithium-ion battery pack, which is installed at a vehicle. And this is the powertrain, and then this is the BL induction motor drive is moving this vehicle, and this is our traction inverter. Okay, so if you double click this one, so here you will get the battery voltage, or you can say DC bus voltage, and this is the SOC curve in per unit. Now let's get back to here and again get back to this window. Now what I am going to do, I'm not going to apply brake. What I am going to do, I am just going to reduce this throttle to 0 and keep your eye onto this LED. See, regeneration is going on, and let's get back to here. See, right now this battery is charging through this drive setup. Okay, through regeneration, and it is going to charge until this is not going to stop completely. Okay, see, regeneration is on. See, the power is flowing, battery is charging. And once vehicle will stop, okay, so charging stop because vehicle is stopped completely. Now let's put some lights. So vehicle is stopped. Okay. Now the SOC is 73.76. Let's stop our vehicle. Means okay. Now we reached the charging station. Now let's charge on. So once we switch on this charging, now the power is flowing from charging station to the vehicle. Okay. And if you want to see, just give me a second. Okay. So this is on. Okay, these are the machine and the vehicle parameters. Let me check with the inverter parameters. So let me add, let me check in the circuit what are the inverter parameters. Okay, so here I can get this VAN in electric vehicle. Okay, but I need to check here. I think so. Okay, so what we need to see, VAB, VBC, battery inverter. Let's get back to this part, and here let's select, let's type VAB, arrange station battery inverter. Okay, and let's see what kind of waveform we are going to have here. Yes, see here, this is the inverter waveform, 5 microseconds. This is okay. Similarly, you can select others also. These are the machine parameters and other parameters. Since vehicle is not moving, that's why everything is showing like that. So you can simply remove also like these things. And when it is charging, you can get the information like say EBC. Like that, you can get, this is the charging. Okay, and once you will switch off this inverter, so this is going to be okay, switch on and switch off, and that type of grid forming or grid following. And let's see the see right now this is working in the mode of grid forming, means the power is transferring from vehicle to grid. Okay, that's why it is showing in red color, because power is going from vehicle to the grid. Okay, so this you know what advantage you are going to have with this one. Sometimes what happens if you face brownouts or blackouts, so in that case your vehicle can power up your home. Okay, so this is showing here. Now next is vehicle to grid. This is vehicle to grid is on. Now let's disconnect this charger and let's run this into UPS. Okay, so this is now charging only. This is just okay. So everything you can do, you can design. We will let you know if you find interesting this one. So we will help you out to design each and everything. Okay. So this is all about this electric vehicle. Now, since this simulation is running since last 8 approximately 7 minutes and 50 seconds. Okay, so let me stop this one. This simulation is continuously run until you are not going to stop, whatever you are using Hail device with this software or not. This software is designed like actual devices. You can play with this one as like physical devices without any danger and without any extra cost. Okay, so let me open one more example, that is a microgrid example. So till that I am opening that model. If anybody is having any doubts or any query, they can ask. Let me get back to schematic editor. Right now, this microgrid model I am going to run into virtual hill mode so that you can get the information that what kind of things are going to have when you are running your model only with this software. Okay, so let me show you. Right now, device is not connected. Just go to home window. See, unable to detect hill device. Earlier, it was detectable. See, hill device is unable to detect. I means unplug the device from my PC. Okay. So let's get back to schematic and open this microgrid example model, then microgrid, and then this microgrid example. So once you will open this example, you will find in this microgrid there are three different kinds of loads are used. One is the voltage behind reactance load, another one is the interruptible load, and next is the constant impedance load. Three different loads are used so that you can change the load profiles, you can create the peak periods, you can add some more dynamics. Okay, and in this microgrid, battery inverter, a battery energy storage system, wind plant, and the solar plant, and diesel generator plant is used to develop this microgrid, as you have seen here. So this is, let's first go through with this one. So this is the energy storage system. If you right click and go to in this mask, double click this one. So here you will find this is having approximately 1.6 MVA power rating and 480 volt line to line voltage. DC link is 1000 and nominal frequency is 60, and it is running on 2.5 kilohertz. These are the filter parameters. Then let's get back to here, and this is our wind power plant. Let's get inside to this one. So here, if you double click it, this one having power rating of 500 kVA and the nominal voltage is 480 volt. Then frequency is 60. Inverter switching frequency, this is running on 10 kilohertz switching frequency, and DC bus voltage is 1000. Disk area is, and you can change any parameter as per your requirement. Wind turbine efficiency, air density, you can change as per your requirement. Okay. Next is the PV panel, PV plant. So just right click and go to look under mark. So here you will find this one. This is having 250 kVA rating with 10 kilohertz switching frequency and 1000 nominal DC voltage, and the PV plant area is 625 square meter, and the PV plant efficiency is 20%. Okay, and this is the filter values. And if you want to see its logic, so you can go inside the mask and you can get the information about the logics and MPPT and other things. You can get all the information here. So for that purpose, means depth idea, you just need to explore this software. Okay, and the last one is the DG plant. So if you see inside the structure of this one, so this is having rating 2.2 MVA with 480 volt line to line voltage and 60 hertz frequency. Okay, and these are the synchronous machine electrical parameters, synchronous machine mechanical parameters, governor and engine parameters, exciter parameters, and rest is controller parameters. Okay, so if you want to see the look under mask, you just go through the block, and here you will find this is the generator, this is the measurement code, and this MCB and grid measurement block. So in control, you will find the logics are developed like power factor control, then exciter start and stop switch. Then this here you will find the exciter. This is a DC4B exciter is used. Then next into this one, governor and engine parameters. If you go to, you will find Day4 governor is used here, and the rest is control mode options, means P mode or Q mode. You can select the modes from SCADA. Okay, and load sharing option, like everything is designed developed here. Okay, and operation mode, you can it's the codes for that one is written here. Okay, So this is the diesel plant. Then next, here it is. Uh, this is the constant impedance load. This is the interruptible load to create peak situation, and this is the voltage behind reactance load. Okay, these are available inbuilt. You can use directly drag from the library. These are available in this loads section. Okay, and again, this is the microgrid controller is developed here. So here you will find the microgrid controller that is having some different situations also, and you will find a lot of things. Testing scenarios also, LVRT or LFRT you can select from here also, or you can create in at SCADA also. Both the options are available. Then next is this is the power PCC monitor, point of common coupling. If you want to see, just go look under mask, and here you will find synchronous check is performed and PQ measurement is done. Okay, so everything you will find. A lot of people are developed their own microgrid using this same model. Means they used same model with their parameters, and they have designed their own control logic, and they have successfully published a lot of papers. Okay, and one patent is also filed with this example from one of industry. That is from Hyderabad, that is Honeywell Hyderabad actually, and they have successfully patented their control logic, which they have developed using this model. Okay, so you can also use the same model for your development. Means just assume how much time you will take to design this complete microgrid. Looking, it's an internal structure. I think it's required approximately 1 month to 3 months time to develop if you are having this model with you. Okay, and if you are not having this model, so in that case, for development of this model, it is going to take approximately 1.5 year time. Okay, so these are available inbuilt. Take the advantage, enjoy the freeness of this software as well as deftness. And with these words, I just like to stop here. If anybody is having any query or any doubts, they can ask.
Hello.
Yes, ma'am.
Good morning, sir.
Good morning,
Sir,
ma'am.
yes, I'm the faculty of electrical department, sir, from G.H. Raisoni College, Nagpur. Sir, I
Yes,
want
ma'am.
to ask one thing, that is this software is available freely, or if I want to purchase it, so what will be the cost of for this sale?
This is, ma'am, first thing, the software means the simulation is completely free of cost. Second thing is,
Hello.
just a second, ma'am, just a second. It's the software is open source. I have given the link. You can give this software to means you can use by yourself also. You can give your students also to utilize. Means unlimited user license you can get with this software. First thing, general license we are giving means you can download anytime from the website, and for advanced license you need to write a mail, because we need to see that you are interested, you are doing some work or not. For that purpose, you just if we find okay you are working, means you are interested to work with this one, so we will provide advanced license in your name, in fact in your institute name, and you can use that license with you to develop your models. There is no cost up till now, but when you want to perform real-time simulation, then you need to purchase one Hill device. Okay, and I am the technical person, so I am not very much aware about the costing. So for costing purpose, you just need to write a mail. I have given the mail ID hill.support@cost.com, or simply you can contact with means if you WhatsApp me, I will give you contact number of the person to whom you can directly interact regarding that purchase part. Okay, but up to simulation, it's a completely free of cost. There is no charge. In fact, whole India can utilize this software for simulation purpose completely free of cost. There is no cost with lifetime updates.
Okay, fine, sir, fine. So can you share your WhatsApp number, sir?
Yes, ma'am. Yes, ma'am. It's a 911-9600-446.
Okay,
there.
fine, sir. Fine, fine. Thank you, sir.
Thank you. Thank you. Any more queries, please?
Okay.
Vijay?
Any
Vi-
queries from participants?
I think there is no queries, and if anybody finds any queries,
Okay.
they can write
I
to
think,
us
sir, there
on
is no
mailbox.
queries from the participants. So
Okay.
thank you very much, sir, for this wonderful and informative session about the
Thank you,
Typhoon
sir.
Health software and hello,
Yes, sir.
sir.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Vijay, sir. Yes.
Hello, Shashank, sir.
Yes, sir. Yes, sir. I'm here. Okay. Thank you all the participants for listening me patiently, and I like to thank you again to Department of Electrical Engineering, especially Professor Vijay Kumar, Vijay Pratap Singh sir, and the HOD sir, and the whole team, whole organizing team, for inviting us into this faculty development program. And I like to wish to whole team all the best, and thank you all. Thank you very much.
Thank you, sir. Thank you very
Thank
much.
you. Thank you. Can I leave the meeting?
Yes, sir. Yes, sir. Yes, sir.
Okay. Thank you.
No problem. So, participants, so next lecture will be scheduled at 12 a.m., 12 noon. So please rejoin us at scheduled time. It's at 12 noon. So this is a half an hour break.